So my talk will be really surfactant polymer flood for potential in a typical Middle Eastern reservoir. We have actually so many reservoirs in the Middle East that are candidate for some type of an EOR process. And I'll just bring one example here. My name is Rida Garbi. I'm actually a senior consultant in the Kuwait Oil Company in the Research and Development Group. I spent almost 25 years as a university professor before I joined Kuwait Oil Company. So my talk today actually has an objectives. I'll show you the objectives and how did we tackle these just to reach these objectives, the methodologies used. What did we do with our management strategies for these type of reservoirs? And then I'll finish that with a conclusion. The objective really is to show how chemical EOR, in this case we have a surfactant polymer flood, could improve the oil recovery from a sandstone reservoir. You're probably aware EOR stands for Enhanced Oil Recovery, and this is just the last step that we take during the production life of an oil reservoir. It starts with the natural energy production. And then after that, we do water flood. We inject the reservoir with waters and until we reach a certain residual saturations of the oil. And then after that, we do some enhanced type of technique, enhanced oil recovery. It could be chemical. It could be miscible gas flooding. It could be nitrogen. It could be hydrocarbon gas injection. It could be CO2. In fact, the reservoir that we have over here, it's a very strong candidate for a CO2 flood. But unlike the US, CO2, we don't have CO2 in Kuwait. So the only means to go is to go for something that we can get. So, so a chemical could be, is one of the processes that will be applicable, in fact, in many reservoirs in the Middle East, not only Kuwait. And that's because we don't have that much CO2. Except a little bit in Abu Dhabi, in areas like that, in which there will be some CO2. As you probably see, CO2 floods all over the world. There are probably about 75 cases worldwide of reservoirs that has been flooded by CO2, and maybe 72 of those are in the US alone. Okay, so because of the CO2 reservoirs that exist in the US. So in Kuwait, we're going to check how this type of chemical EOR will affect our recovery from a sandstone reservoir. So we will be able to determine a reservoir management and production strategies from this particular reservoir. The reservoir actually is a candidate for an EOR process. Okay? Otherwise, we're just going to be, it will be subject to abandonment. So the study will study the effect of the design parameter. We have several design parameters for any chemical EOR process into a reservoir, and we will study the effect of some of those. So how did we start the methodologies here? We have 4 phases. The first phase is we had to collect a lot of data. We did a lot of comprehensive data gathering, from the petrophysical properties to the chemical properties to the fluid types to the porosities to the permeabilities, everything that we can get our hands on, we gathered. Then we built a full field 3-dimensional geological model that we acquire. Then after that, we did a simulation model. We took this whole reservoir that has millions of grid blocks, and we did the model for that, but we can't do all the simulations on these millions of grid blocks. What we generally we take a small sector of the reservoir, and we try to apply that for our process. So we took this whole full field simulation model, and we history matched the production that has been happening since the last 30 or 40 years. That's what we do in generally. We take the reservoir as it is right now, we build it, and then we history match all the production that happens in the past until today. And then we use this model of today to predict what's going to happen in the future. So that's exactly what we have done. That took a lot of our time to reach the phase B, actually to finish phase B. In phase C, which is now the prediction time. So during the prediction, we don't want to, because since we're studying tons, in fact, hundreds of cases, we try to select a small sector that is typical of the whole reservoir, really. We just took a small area in the reservoir that is representative of the whole area, of the whole full field. And then we study different design parameters to maximize the project profitability. And I insist over here, the project profitability is the decision factor here. Because you could, if you don't do economics, what you could do, you could end up with a process that gives you high recovery, but bad economics. So here we included economics just so that we can get the best economic parameters rather than getting the best recovery, okay? So that's what we have done. In fact, I'll show you somehow we did the economic model. So the economic model was based on the estimated recovery. What is the residual oil in place, the oil price? Well, now I don't know the oil prices. When we did this study, after that, the oil prices is really low, so probably we have to go back to these things and look through it again. The operating costs, all of those are implemented to optimize this project profitability. So the way we did the process is it's a model like this that we have a start at the top, then we select a polymer concentration, a given number. We started from small concentrations of 800 ppm all the way to I think to probably close to 4,000 ppm. Then we select surfactant concentrations. We started again from very low concentrations to a little bit of high concentrations. And then we select the total slug size of how much chemicals you need to inject into this particular sector model. And then after that, we did the simulations. Simulations gives us an input. The input goes to an economic model. The economic model, okay, is this slug is a good slug or not? Is it optimized slug size? If yes, we go down to optimize the surfactant concentrations. If no, we go back and select another slug size. That thing is repeated automatically. We let the model works by itself, so a few days of running time. Then we do the surfactant concentrations. If yes, we go down. If no, we go up again to select the new concentrations. And then finally, we optimize the polymer concentration at the end. That's how we really looked at it, because there are so many ways to do this optimization process, but this is the way we selected. So the optimized combines an economic model using the discounted cash flow model, and the measure of the profitability are the net present value for this particular case, the net present value and the internal rate of return. What's a profitability? Well, it's the profitability measures were calculated until an economic model was reached. So what's an economic model? An economic model is defined as the production rate when the EOR production costs exceeds your revenues from the productions. So when you are when you're making money, if you reach below that, if you're not making any more money, that's the economic limit. And that is generally given a number of years. So the reservoir, it's discovered in 1972. It has been water flooded since the early 1980s. Before the initiation of the water injections, the reservoir consisted of 42 vertical producers. Original oil in place for that sector model. We're talking not to the full field. The full field is billion of oil, but the sector model has about 1.3 billion of stock tank barrels. That's based on our material balance calculations. And typical well spacing between one well and the other is about 22 acres. So the depth, the reservoir and fluid properties here, we have a depth about 3,800 feet, temperature about 135 degrees Fahrenheit. It's a sandstone reservoir, and the formation thickness is 100 feet. That's about 50 meters. It's a good reservoir, actually. It has an oil of 31 API, viscosity of 3.7 centipoise, and those are some of the properties that you can see there. This is the sector model that we selected. You can see over here, these are just the permeability maps, or the permeability field of this sector model. As you can see, the permeability changes from zeros all the way till till 600 millidarcies. And the number of grid blocks, they are 135,520 grid blocks, where NY and NX and NZ are listed there. So you have a bunch. This is the one that we did the simulation on, and we tried all the parameters on it. So the prices that we have done, we've done some work some time ago. Now $60 per barrel is not anymore there, so it's unfortunate. It's a little bit down than that. And some of operating cost, we have a 1.3 per barrels. Startup cost for that sector model is 85,000, and so on. We use the royalty of 11% and the inflation rate of 3%. And so just are some numbers that we just picked up from there. This is actually some of the runs that were made, okay? So they are numbered by runs, all the way run one, all the way, hundreds of runs actually. I'm just going to show you a few of them. But you can see the slug that is the second column. It's the chemical slug. That's the total pore volumes that was used for that whole reservoir. It changes from 0.7 pore volumes all the way till 2. We've used a very large number there. Again, the higher it goes, the less the economic profits you will get. The surfactant concentration, again, starts from 0.5 all the way till 0.6 or 0.7. Polymer concentrations from 800 to some more than 3,000 ppm. The chemical cost that we obtain it changes. That's our output, the chemical cost, when we look at all the overall productions, the net present values, and the internal rate of returns. And the last element is the last column is the economic limit, and those are the number of years. Okay? As you can see, the economic limit changes from 9 years, 12 years, 15 years, and that's after that will not be economical. So after we reach those days or those number of years, the process is not economical for this particular case. So continuation of the table, as you can see, the optimum design based on what we have seen, it's a chemical slug size pore volume of 1.2. The surfactant concentration is a small volume, didn't need that much, 0.15, 2,800 ppm for the polymer, and then we have an economic limit of 14 years. 14 years of production using this. This is only the sector model, not the overall the field. So it's, as you can see, the number of the internal rate of return of 35% is extremely, very, very, very economical and very positive. Okay. This is, if you can see, this is we'll put all the results together right now to show you on the y-axis the net present value, and on the y-axis that's in the amount of surfactant. It's in millions of pounds used for these particular cases. Okay. As you can see, the concentration changes for the surfactant concentrations. As you can see, the one with the surface concentration on the top with the 0.15%, that's the one that gives us actually the optimum. If we reduce it further, the net present value comes down, and if we increase it, the net present value also comes down. So we selected, as you can see from there, the surfactant concentration was at 0.115 was an excellent, good number over there to select. Again, this is for a polymer concentration of 2,800 ppm, as you can see in the title. The changes right now of polymer concentrations versus MPV, or MPV versus polymer concentrations, you can see there is a peak somewhere in between, around 2,800, which gives us the optimum salinity for this particular reservoir. And then the surfactant concentration, we picked up the optimum one from the previous graph. And then the final oil, actually, this is the variations of MPV with the crude oil prices. As you can see here, when we are below the zero, that means it's not economical, right? So that means it's about $30 or $35. This process will not be economical to us, period. Okay? But if we are in the oil prices of $70 or $60, and we are making good money there, right? But if the oil prices reaches below that, about $35 or $38, that is not anymore economical, because we're reaching the zero net present values. Okay, this is the oil prices, and this is the NPV versus oil prices, but we are using different realizations. In simulations, generally speaking, we create permeability fields, or we have seismic data that reaches, and then we get those permeability fields. So we create different realizations. It's a seed number, different seed numbers. And every seed number may give you different results. So when you pick up one realization, it may give you different results. So we selected several realizations, actually, so that we are at least know where we are. And no matter what the realizations you have using, I think the oil prices in which you are making good money would not be more than 50. That for realization number 3. For realization, if your reservoir happened to be in realization number 1, you'll be making money at the $35 or $36 per barrels. So that's the actually spectrum of different realizations that plus or minus, and that's the uncertainty that we have to work on. Okay. So let's see what happened here. So the following conclusion may be drawn here from these studies. The detailed data acquisitions and modeling of the reservoir significantly improved our understanding of the reservoir performance. We really understood more right now the reservoir than we have done, or than we at least knew before. The study suggested that on the basis of its characteristics, the reservoir is most suited for a surfactant polymer flood. We could look at other types of chemical processes, for example, an ASP, alkaline surfactant polymers, or by itself surfactant or polymer. We have looked at those, but I think it turned out that the surfactant combined with the polymer flood is a good process here. The history matched identified areas. When we did the history match, we identified certain areas in which we have to do some infill drilling. Infill drilling means you have a nice area in which you did not sweep that, or you did not take that oil from, so you drill over there, and those what we call infill drilling. So with the history match, identify certain areas for infill injection wells and oil targets for the chemical EOR. The most economical design that we have achieved with the surfactant concentrations of 0.15 volume percent, a chemical slug size of 1.2 pore volumes, and a polymer concentration of 2,800 ppm. And the use of high concentrations of polymer and low concentration of surfactant are beneficial for this type of reservoir. That's not true with other reservoirs. But for this particular reservoirs, a high concentration of polymer and a low concentration of surfactants was good enough at least for our interest. And I think that's it. Thank you very much. Okay.